Okay, Bismillahirrahmanirrahim. This is Gulsum Sharifi and I'm a student of BS5. So, my topic is about distributed architecture. So, as it is clear from the name that this architecture, all the system or network component are distributed in different location. They are not in a same place. So, in this architecture, a distributed system is a collection of computational and storage devices connected through a communications network. Here, the computational devices are the laptop, PC, mobile phone, smartphone, printers, etc. And the storage devices are the RAM, ROM, and the hard disk, etc. So, distributed system is collection of these two devices connected through a communication network. So in this type of system, all the component like data, software, and users are distributed. So in this architecture, two important elements plays a very vital role. One is the network topology, and the other one is the communication mode. So the network topology is the way in which the component or the entities are organized to form a connected network, and the communication mode is the method by which components communicate with each other. So these two elements plays very vital role in the distributed architecture. So a distributed system can be modeled by the client-server architecture, which is an example of two-tier architecture, and this forms the basis for multi-tier architecture. Here we will study about the three-tier architecture. So alternatives are the broker architecture such as CORBA and the service-oriented architecture such as web services and grid services. We will cover CORBA too here in this lecture. So there are several technology frameworks to support distributed architectures, including .NET, J2EE, Corba.NET Web Services, Axis Java Web Services, and Globus Grid Services. These are the several technology frameworks that support distributed architecture. So the first architecture we are going to study is the client-server architecture, as it is mentioned from the name. That here is a client, there is a client and a server. These two, I should say, part of the network communicate with each other and exchange pass data. So in this architecture, the client has a process, and same as the server has a process. The client requests the data from the server, and the server replies back to the client and sends back the data to the client. So the client server model is the most commonly distributed system architecture. It is based on two communicating processes, usually running on different processors, and thus decomposes the system into two major subsystems, client and server. The first process is the client that issues a request to the second process, the server, and the server process receives the request and carries it out and sends a reply to the client. As I already told, that client-server architecture is an example of two-tier architecture. So here is the diagram. This is the data server, and this is the client. The client makes request to the server, and server replies to the client. So this architecture has some advantages like separation of responsibilities. Uh, separation of responsibilities such as user interface presentation and business logic processing. Like here, the client has its own responsibility and the user server has its own responsibility. So there is the separation of responsibility. The client is responsible for the user interface presentation, and the server is responsible for the business logic processing. And another advantage is reusability of server components, because because the server accepts many requests of the clients, and there comes a case that many components of the servers are reused. So with the advantages, we have disadvantages too. So the first disadvantage of the client server architecture is lack of heterogeneous infrastructure to deal with the requirement changes, and the second one is security complications, server availability and reliability, testability and scalability, fat clients, representation and business logic. Here, fat client is a network computer with most resources installed locally rather than distributed over a network, as is the case with a thin client. So sometimes it happens that the server are not available, and most of the time server may not be reliable. So these are all the disadvantages of the client server architecture. So this is the example of three-tier architecture. As we studied earlier, with the two-tier architecture comes the three-tier architecture. So this is the example, the diagram of three-tier architecture. Here this is the front-end tier, this is the middleware tier, and this is the back-end tier. Here a middleware tier is introduced. The front-end tier here is responsible for user interface presentation, and the backend tier is responsible for the database management, and the middle tier, which is introduced in this architecture, is manages business logic and execution. Due to the introduction of this middle tier, it has increased the reusability and scalability of the system. So here is the broker architecture. So basically, broker architecture is responsible for coordinating communication between the registered servers and clients. So the broker architecture is a middleware. Middleware, that is, it is in the middle, in the middle of the client and the server, is a middleware architecture used in distributed computing to coordinate and facilitate communication between registered servers and clients. So now let's go with the subcomponents of broker architecture. The subcomponents of broker architectures are broker stub and skeleton and bridges. Stub is also called client-side proxy, and skeleton is also called server-side proxy. Now we will discuss them one by one. So broker, broker is responsible for locating a appropriate server, and this is responsible for forwarding the request that the client makes. It forwards that request to the server, and returns transmits that result and exceptions back to the client. And this also provides APIs for the clients to request and the server to respond, and this is also responsible for registering and registering server components, etc. So here broker coordinates communications, passing on requests and returning replies. The broker states all servers registration information, including their functionality and services, as well as location information. The broker provides APIs for clients to request and for the server to respond, and registering or unregistering server components, transferring messages, and locating servers. So this is the definition of broker. So shortly, broker is responsible for forwarding the request that the client makes to the server, and transmit back the result and exception to the client. And also this provides APIs for the client and servers. This also registers or unregisters the server components for transferring messages and etc. So here is the second one is stub. Stub is also called client-side proxy. Client-side proxy represents layer between client and broker. This layer provides transparency for remote objects that appear local to the client, and there is no independency between a client and broker. This proxy allows implementation hiding, like inter-process communication between client and broker, creation and deletion of memory blocks, etc. So the client side proxy, this mediates. This is, I told you that this is the layer between client and broker. This mediates between the client and the broker and provides additional transparency between them. To the client, a remote object appears like a local one, and the proxy hides the inter-process communication at protocol level, marshals parameter values, and unmarshals result from the server. So the stub is generated at the static compilation time and deployed to the client side to be used as a proxy for the client. So this stub is generated at the static compilation time and it is deployed to the client side. This is in the client side, and the next one, that is the skeleton, that is deployed in the server side. So stub is deployed in the client side to be used as a proxy for the client, and shortly, the stub is a middleware between the client and the broker, and it provides additional transparency between them. This hides the implementation hiding, and between the inter-process communication between the client and brokers is also responsible for creation and deletion of memory blocks, etc. So the next one is skeleton, and this is the server side proxy. This is deployed in the server side. So skeleton and the server side proxy uh, is responsible for receiving requests and unpacking messages and unmarshalling parameters, and also calling appropriate services, marshalling results and exceptions to the client. So these are all the responsibility of the server side proxy, also called as skeleton. So let's go with the description here. Skeleton is also statically generated by the service interface compilation and then deployed to the server side. It encapsulates low-level system-specific networking functions like the client proxy and provides high-level APIs to mediate between the server and the broker. It receives and unpacks the requests, unmarshals the meta arguments, and calls the appropriate service. When it receives the result back from the server, it also marshals the result before sending it back to the client. So these are all the role of skeleton. Shortly, it unpacks messages, it unmarshals parameters. It also responsible for calling appropriate services of the servers, and it also marshals results and exceptions to the client. And this is responsible for receiving requests. And the fourth one is bridge. Bridge, it is a layer between two brokers. It is used to hide each side implementation detail. In particular, when a broker system is run on a heterogeneous network, two brokers have to communicate independently of networks and OS in use. Bridge encapsulates the system specific detail. So, bridge is the layer between two brokers, and it is basically used to hide implementation detail. So, bridges are optional components used to hide implementation details when two brokers interoperate. Bridges encapsulate underlying network detail implementation and mediate different brokers such as DCOM, .NET Remote, and Java Corba brokers. These are the examples of the brokers. They can translate requests and parameters from one format to another. A bridge can connect to different networks based on different communication protocols. So this last line is also very important. A bridge can connect to different networks based on different communication protocols. So shortly, bridge is responsible is a layer between two brokers that is used to hide each side implementation detail. So this broker architecture has some advantages like server component implementation and location transparency. Like that was the role of the broker that provides APIs. And also changeability and extensibility, simplicity for clients to access server and server portability, because the client when forwards the request, so further the broker and forwards the request to the server and gets back the reply. So the other advantage is interoperability via broker bridges and reusability, feasibility of runtime changes of server components, add or remove server components on the fly. And this architecture has these disadvantages like inefficiency due to the overhead of proxies. The proxies like the stub or the skeleton, these two may overhead with each other, and due to that, this is one of the disadvantage. And the other disadvantage is low fault tolerance and difficulty in testing due to the amount of proxies. Now here comes the CORBA architecture. Basically, CORBA stands for Common Object Request Broker Architecture. It is developed by the OMG, Object Management Group, and this is a platform. In short, it is a platform that supports two different types of computing language, and this is due to the ideal that it supports multi-language. So it is also a middleware, neither a two-tier or not three-tier architecture, and it is an open standard for distributed architecture. So CORBA is an open standard for distributed remote method invocation computing schemes. It provides platform and language independent middleware to integrate and distributed applications, including legacy code. And this language and platform independence is due to the ideal interface definition language. CORBA object provides services and operations which are specified in interfaces using the interface definition language, so that clients can make requests without knowing the detailed implementation and location of the CORBA objects. So this all depend on the interface definition language ideal that has enabled the architecture for the clients to make requests without knowing the detailed implementation of CORBA objects. So the CORBA in CORBA architecture, the object request broker, this short for ORB protocol, provides a software bus on the network for brokering the requests from clients and the responses from servers. So between the client and server, there is a software bus that is for brokering the request between them. And this protocol also supports increased interoperability with the with other implementations. So CORBA objects ideal, that was interface definition language, which is a very important part of this architecture, and that ideal is CORBA object ideal specifications are compiled into a stub and a skeleton by the ideal compiler. So by these are stub was the client side proxy and skeleton was the server side proxy, and the stub was deployed in the client side, and the skeleton was deployed in the server side. So these ideal specifications are compiled into stub and skeleton by the ideal compiler. Ideal has its own compiler which is responsible to compile this ideal into the stub and skeleton. The stub is deployed on the client side while the skeleton is deployed on the server side. So the ideal stub has the responsibility. Now both there are two ideal stub and ideal skeleton. The ideal stub has the responsibility to serialize and marshal client request. The stub thus functions as a proxy for the distributed object, and it can receive a local call from the client to the distributed CORBA object. So it talks to its partner skeleton deployed on the server side. So this ideal stub communicates with the partner, that is skeleton, ideal skeleton, and which in turn unmarshals the request, dispatches the request to correct object, and sends the results back to the step on the client side via uh, ORB. ORB is object request broker. So in short, there is ideal in the client side, compiled by the ideal compiler, and also ideal in the server side. In the server compiled by the ideal compiler. These two ideals communicate with each other, and the server and the like the step the client requests and serialize and the skeleton side, in which in turn unmarshals the request and dispatches the request to the correct object. This is the Corba architecture. This is the client, and this is server, and the stub is deployed in the client side, and the skeleton is deployed in the server side. Here is the software bus between the both, and these two communicate with each other. And this is the interface repository. So this is the a short, I should say, simple diagram of the Corba architecture. This operation or arguments, the client requests, and then the server response return value output of the request. So the other one is message broker architecture. So this message broker architecture is a message oriented middleware server in a message oriented distributed system. It performs message routing, message transformation, message invocation, security checking, and exception handling. These are all the role of this architecture. This message broker is short form, is also called sometimes MOM, which is a message oriented middleware. So these are the roles of this architecture, like message routing, message transformation, security checking, method information, invocation, and exception handling. A message broker must be able to route messages from a sender to a receiver based on the content of the message. So a broker can transform a message broker must be able to route messages from a sender to a receiver based on the content of the message. Whatever is the content of the message broker routes that message to the receiver according to the content of the message. So a broker can transform a message from one format to another to meet the different requirements of the sender and the recipient. A broker may also transform a message by modifying, inserting, merging, or removing some data elements in the message. This is the message broker architecture's diagram. This is the application 1, and here is the application 2. It is passing the message, and this is message broker 1. Message broker 1 has the parser, transformer, and router, so it routes the message to the appropriate destination. And here is the message broker 2. It also passed and transform data, and here is the message broker 1 in application 2. This is a simple diagram of the message broker architecture. Now, what are the advantages of this architecture? So the advantages of this architecture are reusability and maintainability, like loose coupling between the client and server components leads to easy maintenance and extension on both sides. And the other one is flexibility in invocation oriented or document oriented messaging. Message heading and body can be altered for a specific purpose. So these two are the advantages of the message broker architecture. So the disadvantage of these architectures include overhead, indirection complexity, and difficulty in debugging and testing due to the new protocol stack added. So we are these are the disadvantages of the message broker architecture. So we are done with the lecture. Thank you so much.